So hello everyone, this is Shivam Rajput back again with a new video on video series of CSR and India for Sciences. So today I'm back with a very important topic, interesting topic, that is collision coalescence process. Now this particular topic is requested by Mr. Ankur, and also I had made a video on Bergeron process. Now this particular topic is there on my YouTube channel. I will give you the link in the description, so kindly have a look on that also. Also, I have very important announcement for you. So on the special request of you guys, I have extended the offer for next 50 students. All you have to do is simply use on the combo course, simply use the coupon code called flat 5500 to get instant discount of 5500 rupees. Okay, now this particular offer is valid for next 50 students only, so do it right now. We are getting lots of registrations, so few slots are left. Okay, so let's start this video. This collision coalescence process. Before starting anything else, I have a question. Why do some clouds cause precipitation and some don't? So right now in Goa, we have cloud, right? In South India, we have clouds. Patchy clouds are there, but there is no precipitation. Why? The reason is the droplets over there are very tiny. They are not big enough to fall. Okay, so here I have a comparison video. You can literally see a difference between a CCN. This is CCN, cloud condensation nuclei, which can be a particulate, a sea salt, aerosol, anything. And the CCN is very important for condensation of a vapor into a liquid or into a solid ice in clouds. Okay, so here you can see this R is nothing but radius of that spherical body of either a CCN or a typical cloud droplet or a large cloud droplet. N is the number of particles per liter, and V is the terminal velocity. Again, it's in centimeter per second. So you can literally see this CCN is very small as compared to a typical cloud droplet. And if you compare this typical cloud droplet with a large cloud droplet, you can literally see the radius difference. It is 50 micrometer. Here it's 10 micrometer. But on the all of that, you can literally see this typical raindrop is 1,000 times, no, 100 times, 100 times bigger than a typical cloud droplet. And the terminal velocity is 650 for this. This V is terminal velocity. So I will discuss in detail what a terminal velocity is. Okay, is this clear? Moving to the next slide. So during precipitation, liquid water or ice that falls to the earth's surface, basically passing through different atmospheric layers, right? Now whenever a water droplet, say water droplet, which we assume is in a spherical form, it start falling down. So basically G is acting downwards due to acceleration, due to gravity. It is falling downward with 9.8 meter per second square. That means in each second the velocity is increasing by 9.8 meter per second. So in each second the velocity is increasing by 9.8 meter per second. That is the acceleration. We know that this gravitational force here depends upon what? It depends upon the mass, and mass itself a constant thing. So mass is the amount of matter inside a body, right? So that will remain constant, no, when it is falling down. So since it is constant, so this mass over here is a function of volume. Density is equal to mass by volume. So we can say that mass is a function of volume, and for a spherical body, the volume is 4 by 3 pi r cube. Simple mathematics. Okay, so this is the formula of volume, a spherical body. So we can say that this mass is proportional to r cube. 4 by 3 pi. These things are constant, no. These things are constant. So it is proportional to r cube. Yani radius ka cube. So radius is what? Say r is the radius. So more the radius, gravity will be more. So it's not the mass. We know that when we drop two things, a big drop or small drop, both will fall with the same velocity in a space. Okay, in air free atmosphere, it will fall with a 9.8 meter per second. But here in our atmosphere we have atmospheric resistance, we have drag force that is acting, right? And that is acting in the opposite direction. So here drag is acting in the upward direction, and this drag force depends upon the rate of fall. So if a body is falling with a greater speed, the drag force will be more. Okay, and if it is falling down with a very slow speed, the drag force will be less. So uh, matlab indirectly we can say that this drag force is also a function of gravity. So if you are falling with a greater velocity, the more and more drag will act on you. At the same time, it depends upon the surface area also. So greater the surface area, more and more wind will interact with the body, right? So more and more air resistance will be there. So during skydiving, what the skydivers do is they simply flatten their body to increase the surface area, and if you have more surface area, you will achieve this drag more. So you will achieve the terminal velocity very fast. Now what is this terminal velocity means? As I told you, this water droplet is having gravity downwards and drag force on upward. So there is a time when this gravity is equal to the drag force. Okay, say after say 3 seconds or 4 seconds of jump from aeroplanes, this skydive was good, this terminal velocity. So what is this terminal velocity? At this velocity you will get a constant velocity. Okay, at this stage you will get a constant velocity. Here I told you the water droplet is falling down with 9.8 meter per second at each second square. At each second it is increasing its velocity. Matlab you can say it falls from helicopter. This is the, say someone is standing here, it is falling down. So in 1 second, say it reaches over here, the initial velocity is 0 and then it becomes 9.8. In another second it becomes plus 9.8. In another second it becomes plus 9.8. Like this it keep increasing. But remember, the drag force is acting upward. Okay, and there is a time when the upward force is equal to the downward force. So at that point of time we will achieve a terminal velocity, and after that say you reach the velocity say 80 meter per second. After that you will fall down with the same velocity throughout the atmosphere. There will be no change, and that velocity is called terminal velocity. Okay, I hope you understand. Now here I told you this drag is a function of what? Rate of fall and area. And what is area? Area is denoted by meter square. So here it is proportional to radius square, length into breadth. Okay, so here it's RQ and here it's R square. Now with increasing size of force of gravity will also increase more than the drag. So droplet will have faster terminal velocity. What it means? So I told you gravity depends on radius q and drag depends on radius square. So say initially the radius is 1. Okay, droplet radius is 1. So square of 1 is what? 1 only. And cube of square of cube 1 is what? Sorry, cube of 1 is what? 1. But as it is moving down, it collide with some other water droplet, raindrop, and radius becomes 2. Say its radius become 2. Now the cube of 2 is 8, while the square of 2 is what? 4. So you can say that gravity is increasing at a faster rate than the drag force. So that means what? So that means the radius is the main factor which decides terminal velocity. Okay, so if you have two particles, say one is having 2 radius and another is having 3 radius, the terminal velocity of this will be more. The terminal velocity of this will be more. Why? Because here the gravity is a function of mass and mass is a function of cube, radius cube. So 3 ka cube is how much? 81, and the square of 3 is how much? 9. So to compensate this 81, the drag force should be more, no? It should be more. So the final terminal velocity will be more. Okay, are you getting my point? You can see like this. Okay, so for a bigger body and for a smaller body, both are increasing at a speed of 9.8 meter per second. Here we have true droplets, 9.8 meter per second. Both are falling down and the acceleration due to gravity is 9.8 meter per second square. Okay, per second square. Say it achieves terminal velocity in 5 seconds only, while here it achieves terminal velocity after 10 seconds. So where we have bigger or huge value of terminal velocity in this case, right? Because in each second you will add 9.8, 9.8. So 9.8, 9.8, 10 times you have to add, right? Then drag force becomes equal to gravity. But over here in 5 seconds only. So 9.8, 9.8 5 times only. Then it become compensated with drag force, right? So here in this case the terminal velocity will be low. Is this clear? Now droplet will fall to the earth when speed of falling is greater than the speed of wind. Okay, so that is again an important thing. So if you have a highest updraft velocity at that stage, the fine droplets will be there in the atmosphere. They are suspended because the vertical updraft velocity is acting on it. Okay, and here the gravity is very weak as compared to the updraft. So that's why they keep suspended in the air for a longer period of time. I hope this is clear to you. Now moving to the next slide. Is this clear? So now these type of precipitation occurs in the warm clouds where temperature of the cloud is greater than 0 degrees Celsius. While in a case of Bernoulli process, those took place in cold clouds where temperature is less than 0 degrees Celsius. They mainly occur at mid-latitude regions or higher than mid-latitude regions. Okay, like in the high latitude regions. While the Coalescence process mainly occurs in the tropical region. Okay. Here the Cesium is hygroscopic in nature. Okay. For this Coalescence process, we need a hygroscopic Cesiums which can attract water molecules, because in this process there is a collision of water droplets only. Okay, so is this clear? Now moving to the next. Here you can see that terminal velocity concept. So basically for a large raindrops, you can see the terminal velocity is very high. This terminal velocity is also known as fall velocity. So both are same. Okay, so here it for large raindrops it is 33. For small raindrops it is 0.001. Okay, so like this. So this is basically a previous year CSR question also. They asked simply based on this concept only. They have given the 4 different types of precipitation forms like hails, and then large raindrops, then drizzles, typical raindrop, and they simply asked about which one has maximum terminal velocity amongst them. So this is to the point question. So it's very important. Okay. Now let's see this one. So as I told you, these occurs in the warm clouds only, mainly in the tropical region, in the tropics, and these type of clouds have only water. There is no ice crystal inside it. For Bergeron there is a ice crystal. Okay, now this water droplet over here is called collector drop. This is called collector drop, CD. Okay, and these are guest guest drop. These small drops are guest drop, GD. Okay, so there are more collision process which is going inside the clouds. We'll see how it occurs. So as I told you, here we have different types of water droplets. Say it's first, this one is second, and this fine one is the third one. Which one has higher terminal velocity? No doubt this one. The collector drop has more terminal velocity than the smaller particles over there. Now as it moves down, it simply increase the high pressure region, because it is compressing. No, see, it is falling down, so it will create a high pressure zone over here, a high pressure zone over here, while this side we have low pressure zones. Okay, in these two sides we have low pressure zone. Okay, so because this collector drop is falling down, so just in front of collector drop you will get high pressure, and here we will get low pressure. So you can literally see over here that from high to low there is a movement of these droplets. But since the terminal velocity of this collector drop is very high, sometimes it also collide with these drops. Some drops are going this way, some drops are going this way, and very few of them collided with this huge drop, these collector drop, like this. So here you should know a term called collision efficiency. So collision efficiency is nothing but it's a percentage of droplet that successfully collide with collector drop. So those droplet which collides with this collector drop, the percentage of that is called collision efficiency. Okay, so relatively large collector drops generally have difficult time in colliding with the small droplets, because it is moving this way, no, because of this high pressure low pressure system. Okay, so these large collector drops move faster than the smaller droplets since it is having high terminal velocity. A region of high pressure will create over here, and it leads to movement of these small droplets outward, but some of them collide with it, and that is called collision efficiency. So relatively these small droplets repelled from the leading edges, it is getting repelled, and here some of them is colliding. Okay, so like this there is an increase in the size. So the collision efficiency increase the size of these raindrops. Are you getting my point? Okay, now moving to the next. So here in this photo you can literally see, here we have this a particle, a droplet, a large cloud droplet, and it is falling down. So if you compare the terminal velocity, it is having higher terminal velocity over here. As it fall down, there is a change in the shape. In general, we assume that the cloud droplets has tear shape, but here you can see these droplets are not in the tear shape. They are slightly, you can say, donut-like structure, oblate donut-like structure. Okay, it's not a tear one. Okay, as it moving down, you can literally see there is some collision, and these collision droplets are known as collision efficiency, discussed before. And as it is moving down slowly, terminal velocity further size is increasing. Okay, and if the radius will change, the terminal velocity will change. It will never be the same because it depends upon the radius. So here you can see now it is falling with a faster speed, and finally this larger raindrop breaks into the several small drops which grow again by acceleration. So after this process, it will return to step number 1, then 2, then 3. So all droplets will follow the same process then. Are you getting my point? It's a cycle. It will keep doing this, and unless and until it will reach the surface. Now, sometimes you feel that the droplets of the rainfall is very very huge. That means that the terminal velocity is very high, and sometimes you will see a drizzle kind of rains. So over there terminal velocity is low. That means they have not sufficient time to increase the terminal velocity. The cloud length is less, you can say. So these are some assumptions. On the basis of that you can understand collision coalescence process. By the way, this collision coalescence process is different from Bergeron. Over there there is a more growth on the ice crystal as compared to the water droplet, while over here there is a more growth on the water droplet. Again you can compare that those Bergeron process occurs in the cold clouds where temperature is less than 0 degrees Celsius throughout, which is having those clouds are having ice crystal and super cooled water droplets. Super cooled water droplets is nothing but if the temperature is below minus 40 degrees Celsius at that point of time, there is no need of CCN, and they are also you can form a cloud droplet without CCN at minus 40 degrees Celsius. So those clouds are having sometimes minus 40 degrees Celsius temperature, and these are called super cold cloud droplets. So here it's different. It's a warm cloud. It is taking place in the tropical regions. Okay, in India mainly we have this kind of precipitation. Okay, so yeah, this is the difference between collision coalescence process and your Bergeron process. Also, the in the Bergeron process we have low clouds, while in the this in the collision coalescence process we have the low clouds, which is having more horizontally expanded, while in the Bergeron process we have cumulonimbus clouds, vertically elongated clouds, cumulonimbus, and these are horizontally small while vertically elongated, and most of the regions of droplets formation is mainly above the level of condensation, LOC. So before LOC only you will see there is a formation of those ice crystals, and whole Bergeron process will occur above LOC, while in these clouds most of the collision coalescence will takes place below LOC, because above LOC we will have temperature less than 0, no, below LOC the temperature is more than 0, and here collision coalescence process will take place, CCP. Okay, so are you getting my point? In Bergeron process the mechanism occurs above LOC, above level of condensation, and in collision coalescence process most of the processes occur below LOC, that is your CCP, collision coalescence process. Okay, so that's it for the today. Hope you like the video. Kindly check out the course which is there on the YouTube. You will get the link in the description also. So that's it for the